Okay, hello everyone in a new video. So we have reached part 2 of chapter 6, which is the chapter of AC voltage in the second of electricity. And the title of this section is given by, okay, so we have reached section number 6. And the title of this section is given by indications of different electric components. Sorry, of different electric sources. And here let me start by this document. So in this document we have the following indication, and we know that this indication correspond for the, so let me say is the indication of a DC voltage source now. What about this indication? So this indication, so here we have the waveform of a voltage source, and we know that this represents the AC sinusoidal voltage source. So let me write down as the indication of a AC alternating sinusoidal voltage source. As for this one, so this is also alternating, but instead of sinusoidal it's triangular. Sorry, it is so it is a square. So let me say is the indication so here let me say of an AC alternating square voltage source. And as for the last one, notice that in this case it is an AC alternating a triangular voltage source. Okay, so now let's move to the next section, which is the normal functioning of a lamp under an AC voltage source. Let me write down the title of this section first. An AC voltage source. So the title of this section is given by the normal functioning of a lamp, not necessarily a lamp but any other electric component. So whenever we want to describe the functioning of the lamp, this is done by comparing the applied or traversed voltage current respectively to the rated values of the lamp. So now in this case, if we consider this simple electric circuit, so we have a voltage source connected to a lamp. Now from the indication of the voltage source, one can notice that the type of this voltage is given by AC alternating sinusoidal voltage source. So in order to describe the functioning of the lamp, we need to compare the value of the voltage, applied voltage, to the rated voltage of the lamp. But here the problem is that we have two values for this voltage. We have the maximum voltage and we have the effective voltage. Okay, so in order to describe the functioning of the lamp, we always consider the effective voltage and not the maximum voltage. Okay, so let me write the following. So given a lamp L with the following indications. $12 volts. So what does this indication represent? The rated voltage of the lamp L under which it functions normally. And let me pose the following question and say, how does this lamp functions under an AC voltage? So in order to describe the functioning of the lamp, we need to consider the following steps. So step number 1 is to find the effective voltage U effective of the given AC voltage source So the first thing to do in order to describe the functioning of the lamp, we need to determine U effective, and we have seen previously how to determine U effective. First we determine UM from the oscilloscope, then U effective is related to UM in the case of AC sinusoidal voltage source by square root of 2. Now step number 2, we have the following cases. So let me write the first case. If the effective voltage is less than the rated voltage of the lamp, then the lamp L in this case, as we have seen previously, may not function or function weakly. The second case that we need to consider, if the effective voltage is equal to the rated voltage of the lamp, then the lamp L will function normally. Now the third case also that we want to consider, if the effective voltage is greater than the rated voltage of the lamp, then the lamp L may function strongly or burns out. So now the other section related to this idea also is the usage of the voltmeter in the AC mode. So let me write down the title of section number 8, which is given by usage of the voltmeter in the AC mode. So always one must distinguish between the effective voltage and the maximum voltage. Now if you consider this document consists of a simple electric circuit. So here we have the generator G. Connected to the generator we have the lamp L, and connected in parallel with the generator for sure we have the voltmeter. So notice that the first thing is that here the COM terminal is not labeled simply because the COM terminal is related to the positive and the negative pole, and we have said previously that in the case of AC voltage source, as indicated here, we don't distinguish between the positive pole and the negative pole. For this reason, the COM terminal usually in the AC, in the case of AC, in the case of the generator delivers an AC voltage, we don't indicate the COM terminal, okay? But now we are interested in determining the reading of the voltmeter. So here the voltage source is described by two voltages, and they are given by UM and U effective. So in this case, what does the voltmeter reads, UM or U effective? So it simply reads U effective because it is the voltage that makes the effect. So let me write down a voltmeter in the AC mode. So the voltmeter functions in two modes. Here the functioning is in the AC mode, connected across an AC voltage, source U, which happens to be in this case, measures the effective voltage which is given by U effective of this voltage source. Now let's consider the adjacent figure. The voltmeter V is connected across the terminals of an AC. In this case, this is not any AC voltage, but rather AC alternating sinusoidal. Voltage source. Then the voltmeter measures the effective voltage U effective of the given source. Okay, so in this case, the voltmeter is measuring the effective voltage of the given source and not the maximum voltage. So now, as you can see, we are repeating the same steps or the same ideas that we have discussed in the DC voltage. Now let's solve the following exercises as a direct application on what we have explained. So this is exercise number 2, section 9 in this chapter. They are telling me an AC alternating sinusoidal voltage source delivers a voltage of maximum value UM is equal to 210 volts. So here let me write down directly that UM is equal to 210 volts, and here whenever we have the value of UM, we can directly determine the value of U effective is connected directly to a lamp L. So this voltage source is connected directly to a lamp L, carrying the following inscription 140 volts. So what does the inscription of this lamp represent? It is the rated voltage under which the lamp functions normally. Now they are telling me, does the lamp L functions normally? Justify. So in order to describe the functioning of the lamp, we need to compare the voltage, the applied voltage with the rated voltage. But here, because the source is an AC sinusoidal voltage source, we have two types of voltages. We have the maximum voltage and we have the effective voltage. So in order to describe the functioning of the lamp, we need to calculate the effective voltage and not the maximum voltage. Okay, so first let's calculate the effective voltage, which is given by UM divided by radical 2. So always refer to the effective voltage and not the maximum voltage whenever we need to describe the functioning of the lamp. And the maximum voltage in this case is given by 210 volts. So 210, and here they are giving me that the value of radical 2 is given by 1.4, so divided by 1.4. Now plugging this fraction on the calculator, we get that the value of the voltage is given by 150. Since UM is expressed in the SI, which is volts, then the value of U effective will be in the SI, which is volts. So U effective is equal to 150 volts. Now after we have determined the value of U effective, in this case U effective represents the applied voltage, now we are able to describe the functioning of the lamp. So notice that 150 volts is greater than the rated voltage of the lamp, which is 140, which means that the lamp may function strongly or burn out. Since the applied voltage, which is the effective voltage, is greater than the rated voltage of the lamp L, which is because 150 volts is greater than 140 volts, then the lamp L may function strongly or burns out. Okay, so this is it for exercise number 2. Now let's move to exercise number 3. They are telling me an AC alternating triangular voltage source, and here let me correct the following and let it be sinusoidal. Okay. An AC alternating sinusoidal voltage source delivers a voltage U of maximum voltage, UM is equal to 200 volts, is connected directly to a lamp carrying the following inscription: 210 volts. So now, previously the indication of the lamp is given by 140 volts, now 210 volts. Does the lamp L functions normally? Justify. Take square root of 2 is equal to 1.4. Now, at the first glance, one thing that 210 volts is equal to 210 volts, which means that the lamp will function strongly. But recall that in order to describe the functioning of the lamp, we need to calculate the effective voltage, which is given by UM divided by square root of 2, which is given by 210 divided by 1.4. And in this case, the value of the effective voltage is given by 150. Since UM is expressed in the SI, which is volts, then U effective will be expressed in the SI, which is volts. Now, after we have determined the effective voltage, now we are ready to describe the functioning of the lamp. So notice that in this case, U effective, which is given by 150 volts, is less than the rated voltage of the lamp, which means that the lamp may not function or function weakly. Since the applied voltage is less than the rated voltage of the lamp L, which is because 150 volts is less than 210 volts, then the lamp L may not function or function weakly. Okay. Now, as for exercise number 4, section 11, they are telling me a voltmeter in the AC mode is connected to a source delivering an AC alternating square. So please also let's correct the square and make it sinusoidal. Of maximum voltage UM is equal to 140 volts, take square root of 2 is equal to 1.4. Now in number 1, they are telling me draw an electric circuit illustrating the above experiment. So the electric circuit consists of two components: the voltage source delivering an AC voltage, AC sinusoidal, and the voltmeter. So it only consists of two electric components, the voltmeter and the AC alternating sinusoidal source. So let's start by the AC alternating sinusoidal voltage source, and we have seen that its indication is given by this. So this is the AC voltage source. Now connected to this source we have the voltmeter. Here we are free to connect the voltmeter from above or even from below. Okay, so let me consider that it's connected from below like this. Now in this case we don't have a closed circuit, in a sense that no need to connect these terminals together. Now what about the COM terminal? Recall that here we are measuring an alternating voltage, which means that these two terminals are alternately positive and negative after a certain period, so no need to place the COM terminal. Okay, now in number 2, what will be the indication of the voltmeter? So here by the indication of the voltmeter it means the value of the voltage, but notice that this voltage source is characterized by two voltages and they are given by UM and U effective, but we always consider U effective because it is the voltage that makes the effect. So now let's calculate U effective, which is equal to UM divided by square root of 2, which is equal to 140 divided by 1.4. Now plugging this on the calculator, then the value of the effective voltage is given by 100. Since UM is expressed in the SI, so the value of U effective will be in the SI, which is volts. So U effective is given by 100 volts. Then the indication of the voltmeter is given by 100 volts. So this is it for exercise number 4. Now let's move to the other section, which is the variation of the voltage with respect to the sensitivity. And let me write section number 12, which is given by variation of the voltage with respect to the sensitivity. And here let me start by the subsection 12.1 and say variation of the DC voltage with respect to the vertical sensitivity as V. So here in the following cases, we have the screen of the oscilloscope, and in this case, the measured voltage is a DC voltage source. In this case, it's positive, also here and also here. But in each case, the number of divisions is different. And now let me say the following as the horizontal sensitivity, sorry, here it must be the vertical. So as the vertical sensitivity decreases, the luminous line is shifted upward. Now here let me write down the vertical sensitivity in each case. In this case, the value of y is given by 0.8 when the vertical sensitivity is adjusted to 3.5 volts per division. Now in this case, the value of y is given by, if this is 1.2, 1.4, 1.6 divisions, when the vertical sensitivity is given by 1.75 volts per division. And in this case, the value of y is given by 2.8, if this is 2.2, 2.4, 2.6, 2.8, when the vertical sensitivity is given by 1 volts per division. So as you can see here, when as we move on, as the value of the vertical sensitivity decreases, so here the value of y is given by 0.8 divisions. Y is equal to 1.6 divisions, and here the value of y is given by 2.8 divisions. Now as you can see, as the value of SV decreases from 3.5 to 1.75 to 1, the value of y increases. Okay, so this is an important property, and this can be seen from the formula, which is given by U is equal to SV multiplied by y. Because if you construct the triangle of this formula, here notice that there is no the label M because this is for DC voltage. We have U as V multiplied, this is Y. So notice that in this case, SV and Y are neighbors living in the same floor which hate each other, which means that they are inversely proportional. As SV increases, the value of Y must decrease, okay? And now let's refer to the case of the AC voltage, and let me write here section 12.2. Variation of the AC voltage with respect to the vertical sensitivity as V. And here, before I write the result, let me approach this problem in the following way. So here we have 3 documents. So in this case, let me write the values of x and y. So here the value of x is given by 2 divisions, and the value of y is given by 1 division, because x represents the number of divisions between 2 consecutive peaks, in which y represents the number of divisions from the center to the maximum. In this case, x is also given by 2, whereas the value of y is given from the center to the maximum point. In this case, y is equal to 1.8. And in this case, x is also given by 2. So the number of divisions between 2 consecutive peaks, and the value of y, which is given by 3.2. Now, according to these configurations, the values of SV are given by, in this case, we have 3.2 volts per division. In this case, we have the SV is equal to 1.78 volts per division. We have SV is equal to 1 volts per division. And as expected, as the value of SV decreases, the value of y increases from 1 to 1.8 to 3.2, because recall that according to the following formula, UM is equal to SV multiplied by y. As V and Y are neighbors living in the same floor, which means that they hate each other. As V increases, or as V decreases, the value of Y must increases as it is happening here. As V decreases from 3.2 to 1.78 to 1, which means as V is decreasing, we expect that the value of Y must increase from 1 to 1.8 to 3.2. Okay, but notice another important thing, that the value of X remains the same in each of the following cases because X is related to the time base, or SH, and it is not related to SV. Now let me say that as the vertical sensitivity decreases, the number of divisions Y corresponding to SV increases. And now, as for the next section, which is given by 12.3, which is given by variation of the AC voltage with respect to the horizontal sensitivity. VB. So now let's pick up the values of X and Y for each of the following cases. So let me say this is X and this is Y. So notice that X is the number of divisions between two consecutive peaks, and this is given by 2 divisions. And in this case, the value of Y is given by 1 from the center to the maximum point. In this case, this is X and this is Y. X is the number of divisions between two consecutive peaks, and in this case is given by 1, 2, 3. As for the value of Y, it's from the center to the maximum point, which is given by 1 divisions. This is X, this is Y. In this case, X is the number of divisions between two consecutive peaks, is given by 1, 2, 3, 4. And as for Y, the number of divisions from the center to the maximum, which is given by 1 divisions. And this configuration corresponds to VB is equal to 2 milliseconds per division. This configuration corresponds to VB is equal to 1.67 milliseconds per division. And this configuration corresponds to VB is equal to 1 milliseconds per division. So here what do we notice is that as VB decreases from 2 milliseconds to 1.67 to VB is equal to 1, the value of X changes from 2 to 3 to 4, which means that as VB decreases, the value of X increases. And this is clear because if we refer back to the formula, we know that VB is equal to, we know that T is equal to VB multiplied by X. So constructing the triangle of this formula, the period at the top, VB and X at the bottom. So notice that VB and X are neighbors living in the same floor, which means they hate each other. As VB decreases, X will behave in an opposite manner, which means that X will increase because they are inversely proportional. And here let me write down as the horizontal sensitivity decreases, the number of divisions x corresponding to VB increases. Okay, what about the value of y? So notice that here what we have changed is the value of VB, and we didn't mention anything about SV. We know that y is related to SV because we didn't change SV, so we expect that the value of y must remain the same, which is given by 1 division. And that's it for me in this video, guys. By this we have finished section number 12. In the next part, which is part 3, we'll complete the explanation of this chapter.